So I'll show you them.
Yeah, so this talk is about perturbation theory. So the kind of philosophy here is that if you pick a random nonlinear differential equation out of a hat, you probably can't do anything with it. Like there's very few isolated points where you can exactly solve things like Parametric equations or Ecalle equations, but for the most part, there's no closed form solutions, there's no solutions as integrals, and so we resort to perturbation theory. So we try and understand solutions to these things in some large or small region of the variable. And this is, of course, much easier. So you can take any one of those equations and posit some expansion for large Z and start solving for the coefficients to generate an approximation. And Taylor's theorem ensures that this will be at least asymptotic to the true solution. But it's not the end of the story because, Taylor's theorem tells the remainder is algebraically small, whereas hidden in this expansion can be exponentially small terms, like these e to the minus Z terms, these non-analytic terms. I'll explain where these come from as we go. And part of the point that I want to get across in this talk is that there's a really nice mathematical structure to perturbation theory. And via resurgence, you can kind of think of asymptotic expansions as just analytic attenuation plus geometry of Riemann surfaces. And I hope that perspective will be clear by the end. And actually, for the most part, I'm going to focus on singly perturbed equations. So just a random example there, that Ecalle type equation, epsilon y prime plus y squared is 0. So you're thinking of epsilon as small and z as some finite variable. I'm going to look for asymptotic expansions to these kind of things. Yeah, and these kind of, so we have these expansions, algebraic expansions plus exponentially small corrections. So on the left here, you think of G as some small parameter. You get algebraic series plus exponentially small corrections, and these so-called trans-series expansions show up all over the place in applied math, from quantum field theory, where the algebraic bits are Feynman diagrams and the exponentially small bits are solitons, through to free surface profiles, which is what I'm going to talk about today. Good. Yes? Trans-series. I will have a definition in a second, but roughly it's just like some algebraic formal power series, so just an algebraic series in a small parameter, plus exponentially small corrections. And we're going to focus on these things called log3 height 1 trans series, so expansions of this form with g squared, and then e to the minus 1 over g. So we're going to look for solutions, expansions of that form to solutions to the differential equations. Yeah, and that restricted space of trans series has a nice geometric interpretation, as we'll see. Yeah, do interrupt me if something's not clear. So let me just give a little bit of motivation. This is the kind of toy problem that I'm going to think about towards the end of the talk. So I'm studying 2D fluid flow, incompressible, inviscid, so we're just solving Laplace's equation. And the setup on the right there, can you see the mouse? Yeah, this setup here. So I'm going to think about flow over some bed, and the bed geometry is going to be determined by me. And then we're going to be solving for the free surface and seeing the effect that the bed geometry has on the free surface. And we're going to be finding trans series expansions of this free surface, where the small parameter is going to be the free number. So let me just rapidly kind of review this boundary integral formulation. If this isn't familiar, the upshot of this construction is that we end up with some nonlinear ODE to solve. But the idea is that you can apply a sequence of conformal maps. So you first work in the potential plane, where you have the free surface at some determined position, and the bed geometry is along the bottom in the potential plane. And then we switch variable to this zeta, equals e to the minus w, and introduce some this so-called holograph variable q and theta. And the upshot is that you can write this problem as a coupled integral and differential equation. So this Bernoulli's equation in these new variables, and this is imposing essentially the potential is holomorphic. So this bit is solving Laplace's equation. Essentially, the toy problem that we end up with is some nonlinear singly perturbed ODE. So if that derivation is not familiar to you, this is the kind of equations that we're going to be solving in the talk. So epsilon there is essentially the free number. Q0 specifies the bed geometry. So if I have a different geometry on the bottom, I have a different Q0. And then Q is essentially going to be my free surface profile. So we're going to be looking for trans-series expansions to that nonlinear differential equation. And the different terms in the trans-series are going to tell us about the ripples that turn on. I mean, the idea is that when you have a step on the bottom, the free surface passes have some ripples that are turned on. That's something called Stokes phenomena. Okay. And the main example that I'm going to look at is the case of just sharp corners on the bed. And so whenever we have a sharp corner, we're going to find some ripples. And the higher terms in the trans series are going to be corrections to those ripples. I'll explain that in more detail as we go. Okay, so let me do a quick recap of Stokes phenomena. May or may not be familiar to people, but the basic idea is that just to fix an example, let's think about this linear differential equation on the left. And what you can do is seek a power series solution to that equation. So you make an ansatz like f equals a0 plus a1x plus a2x squared, and you start to solve for those coefficients. Okay? And what you'll find is that an is n factorial. And so if you put all those coefficients together in a power series, that thing diverges. And in general, if you have a differential equation or linear differential equation with an irregular singular point, this is what it means. It means the power series will diverge. And so you need to somehow, well, we're going to see that there's a way still to assign analytic meaning to these divergent power series solutions by resumming them. But for now, let me just say that Taylor's theorem ensures that this approximation is asymptotic to the true solution. So it doesn't converge to the true solution, but if you fix n and let x be small, then it's a good approximation, which is the opposite of convergence, which is where you fix x and let n. Poincare asymptotic is the true solution. But the point here is that if you look at the proof of Taylor's theorem, it applies to an interval, or like a half interval, which in the complex plane translates to some sector. And so it need only be close in a fixed sector of the complex plane. And as you move around to different sectors in the complex plane, the asymptotics can jump. And it can jump by these exponentially small terms I mentioned earlier. And that's the basic idea of Stokes phenomena, is that in different sectors of the complex plane, you have different asymptotic expansions. I think I'm going to skip the discussion of optimal truncation for now. So, yeah, or maybe I'll say a little bit. So, yeah, what can happen is that as you walk around the complex plane, exponentially small terms can enter the asymptotic expansion, and they'll be small along these things called Stokes lines. And as you walk around to anti-Stokes line, they can come to dominate the asymptotics. And this can have real physical applications. So you can have, say, a Stokes line in the complex analytic continuation of your free surface that then intersects the free surface. And on either side of that Stokes line, you can have an exponential term, i.e. oscillations, or just a waveless free surface on the other side. Okay. So one perspective of understanding these so-called trans-series expansions is this idea of resurgence. So, yeah, think of this bit of the talk as kind of just a tutorial on this old story of constant resurgence. So there's nothing new here, but let me fix this equation in a box just so we have something to look at. And I want to find asymptotic expansions to solutions of this equation. And what we're going to find is that near infinity, that asymptotic expansion is going to jump across these Stokes lines. So you posit an algebraic expansion like this, and you can imagine sticking that into a differential equation and starting to solve the coefficients. I mean, you'll find the first one is 1, the second one is -1, the third one is 2. That's normal asymptotics. And actually what we obtain, and it's not too hard to prove, is that we obtain something called a Gevrey-1 asymptotic series, which means that the coefficients yn are bounded by a factorial. So they only grow as large as a factorial times a power. And in that case, what we can do, it's kind of a funny thing, but it's called this Borel transform. And what the Borel transform does is it takes your divergent power series and you just divide every term by a factorial. And so the thing that you end up with, this yb, is now a holomorphic germ of a holomorphic function. So you get something that converges just by dividing out the divergence. Okay. And I've underlined the word resurgent here, and what this means is that in nice cases, and for differential equations with, say, polynomial coefficients, the germ that you get in this way, if you walk it around the complex plane, you can always go out to infinity and only have to dodge finitely many singularities on the way. So it has a nice analytic continuation. And for us, actually, we're also going to work in the context where the singularities that you find when you analytically continue this guy are only going to be branch points or poles, nothing more exotic. Okay, so what's the point of that? The idea is that once you obtain this germ, you can perform this integral over the germ, over some contour. And if I say, to begin with, let's say that contour is 0 to infinity, and imagine sticking in that power series expansion into that integral, what you'll find is term by term the integral formula for the gamma function. And so what this does is it puts back in the factorial divergence. So the idea is that yz here is perfectly convergent analytic function, but along the real axis, it has the same asymptotics as the y that we started with. And this is the procedure of Borel resummation, where you take a divergent thing, divide out the growth, and then do an integral transform. And this yz has the same asymptotics as the thing we started with. But it has a wider range than z. I can walk z around the complex plane, and it defines for me a holomorphic function. Does that idea make sense before I go further? Or any questions?
You sort of doing an analytic continuation of the original series.
Yeah, exactly right. Yep. Exactly. Yeah, if you get like a Stokes-Levy one asymptotic series, which has it grows, it diverges, but not too badly, you can divide out that divergence and define an integral that's analytic but has the same asymptotics as the thing we started with. And then you continue that thing. Exactly right. And if you have a differential equation underlying all of this, that process kind of commutes, so you actually know that you've got the solution. Yeah, exactly right.
Is this general
super general story?
For any divergent series?
Any divergent formal power series that has Gevrey 1 asymptotics.
Okay,
or,
now this,
yeah.
So it has to have this.
Or Gevrey P even. So
yeah.
Powers of factorial growth. Yeah, exactly.
Quite common.
Very common. And it's kind of universal in the sense that if you have a singularly perturbed problem where like each term in your power series is given by differentiating another one, you automatically get factorial growth from that. So it's universal in that sense. Yeah.
You need to be careful about the choice of gamma naught.
You need to be very careful, and that's exactly where Stokes phenomena enters. Exactly right. So yeah, if I take gamma naught to be 0 infinity, this integral converges. Oh, where's the picture of this? Just below. So exactly that. So the idea is that initially gamma naught is 0 infinity, but as I move z around, I need to move that contour around in order to keep my integral convergent. Because as it stands, this is kind of, that'll be convergent in the right half plane. But as z goes up, I need to move my contour with it. So imagine walking around z. But then I run into an issue. If this germ yb has a singularity in its analytic continuation, I can run into an issue because like I walk z around, my contour comes with me, and here I suddenly snag on chi. And if I want to compute on this contour versus this contour, I have to subtract off this integral. And that's Stokes phenomena, because if I integrate around that, it's a Hankel contour. If I integrate around that Hankel contour, say that this chi, so I have a germ, I analytically continue it, and I find some branch point singularity at chi. So it looks locally like W minus chi is the max gamma. Gamma is some rational number, say. And the point is that this Hankel contour, if I do this integral, it's just kind of like this is more or less an inverse gamma function. A reciprocal gamma function. After some change in variables, what you get is this term, which is an exponentially small correction. So for 0 infinity, I use my formula for the integral formula for the factorial, and I get the formal power series I started with. If I go past here, I get this term entering the asymptotics, which is exponentially small and z is large. And you can see that the nature of the singularity in the analytic consideration of the Borel transform determines everything in the trans series. Like the gamma is the local power of that singularity. So this has an algebraic bit as well. And then the chi is the location of the singularity. And that's called a trans series. So the algebraic asymptotic expansion plus all these possible exponentially small terms that come when your contour snags on singularities. And yeah, the locus along which this happens, so you can imagine as you walk around with a Z, there's a certain line along which my contour snags, and that line is called the Stokes line. Okay, does that make sense? So, yeah, maybe I'll tell you this bit first. So, I haven't really told you what resurgence is yet, so where the word resurgence comes from. Yeah, so there's this important idea which is Darboux theorem, which is, I'm just doing complex, basically undergraduate complex analysis here. Forget all the asymptotics and just think about complex functions. If you have some power series with some singularity rho on the, well, it doesn't have to be on the unit disk, just some distance rho, you can study the asymptotics of the power series expansion as n is large. And what you find is that the asymptotics of the power series coefficients know about the nearest singularity. That's just a fact of complex analysis. And in fact, it's a really easy fact because you just take each term here and do a binomial expansion and look at the nth coefficient in S and you'll find the asymptotics when it's large. So yeah, relatively mundane facts in complex analysis. But if you translate this, the Borel transform framework, what you see is that, I mean, imagine where these coefficients are coming from. In the Borel transform, they're coming from the perturbative solution, so a differential equation, just the algebraic series. And if you study the asymptotics of those, they know about this nearest singularity, and therefore they know about their own corrections. So that's the magic of resurgence, in the sense that perturbation theory actually knows its own exponentially small corrections. If you have an all orders Chevreul asymptotic series, you know what the Stokes lines are, and you know what the extra contributions are. Yeah. Okay. Does that idea make sense? That's the sort of key, maybe the key point of normal constant resurgence. Yeah. I think this is sometimes seen as kind of an esoteric area of maths, but yeah, one of the goals of this work is to show how we can actually use this in applications. So we'll get on to back to the water-wave problem in a second. One thing I just wanted to say is that a lot of people in kind of applied exponential asymptotics get put off by the Borel transform. I don't know, maybe it seems a bit complicated, but it's just a Laplace transform. Okay? So this integral that I wrote down is just a Laplace transform with respect to the large variable z. So what you can also do is just seek a solution to your ODE in the form of such an integral. And just like integral transforms, you get some effective equation for the Borel solution YV, and you can study that instead. The tricky thing is that when you have a nonlinear ODE, things are much more complicated, but I mean, in a precise way, in the Borel plane, in that you obtain from y squared terms, you can maybe imagine you get a convolution out of this, when you have a W integral, you get a convolution. And what happens is, if I have my one singularity chi in the Borel plane, it gets multiplied to 2 chi, 3 chi, 4 chi. Which you can also see from the trans series. If you imagine making an ansatz of like y equals minus e to the minus chi, you've got a y squared, you're forced to include 2 chi, 3 chi, 4 chi. So the trans series has lots of extra components if you have a nonlinear problem. And typically, one of the points here is that in kind of applied exponential asymptotics, people typically study this chi. And of course, if you're thinking of these as Fourier nodes in some free surface profile, these chi, 2 chi, 3 chi are then the higher Fourier nodes in some way. So it's kind of important to study, or can be important to study these higher trans series components. Okay. I only have 40 minutes, right? So maybe I'll. Okay. Okay. Let me move to parametric problems then. So now I'm going to think about trans series where you have a small parameter epsilon and some finite variable z, and these are kind of what come up in applications all the time. This is singular perturbation theory. And now our trans series looks a little bit different because I don't have numbers in the exponential, but now I have functions. And my algebraic series are no longer just numbers in epsilon, but they're formal power series in epsilon with functions, holomorphic functions. And in the Borel plane, we have singularities whose location now depends on z, and the algebraic corrections depend on z. Okay. And now the Stokes line picture is a little bit different because now you have the Borel plane. So when you take your formal power series, which has coefficients, functions, and you divide out by the factorial divergence, you now have a parametric Borel transform in that the singularity locations in the Borel plane all depend on z now. So what you have is a fixed contour here to go. So this is how you go back from the Borel transform to a trans series as you integrate along here. And then you have issues, or you have Stokes lines, whenever these singularities come down with a snag on the contour. Then you have a locus in your physical plane. This could be a free surface. Then you have singularities in your continuation. And when you cross from left to right, it's where these snag on the Borel plane contour. The essential new feature that we find in this case, in these parametric Borel transforms, is that there's now two types of singularities. So you have these Borel singularities that I talk about, which we think of as maybe branch points or poles. But we also have the so-called physical singularities, which are singularities that appear in the terms of your epsilon formal power series. And the key difficulty of singular perturbation theory is how these two types of singularity play together. Does that setup make sense? Okay. So one of the things that we've developed here is this kind of holomorphic Borel plane inner-outer matching. So as I say, you have the Borel singularities that are your kind of exponents of your trans series, and you have the physical singularities. And when you move towards these, your Borel singularities come to the origin. But what you can do is define a new variable on the Borel plane, this S, W over chi, and separate everything out. So now that things are fixed. So W is chi as a singularity, but now it's S is equal to 1. And this allows you to make progress with matching. So because this Borel plane, because this parametric Borel transform depends on two variables, you now have a choice on how you expand it, which we didn't have before in the constant case. So you can either expand near the Borel singularities, or you can expand near the physical singularities. And the way that these two expansions compare to each other gives you a relationship between two different things. So you have, remember each term here is the kind of, so you have an exponential from this S, and e to the minus chi over epsilon, and each term here is an algebraic fluctuation around that exponential, and you've had to get your hands on these. What we can do is further expand these near the physical singularity, or expand these near the Borel singularity and compare the two. And when you do an inverse Borel transform, to go back to asymptotics, what you get is a proof of Van Dyck's rule, which maybe you're familiar with, perhaps, from matched asymptotics. And in this setup, in the parametric Borel plane, Van Dyck's rule is just expand the holomorphic function two different ways and compare the expansion. So, yeah, let's go back to a concrete example for the last 10 minutes or so. So, this is kind of a slightly reduced toy water wave model, which is kind of related-ish to the problem I showed you earlier. So you have flow over a step, and there's some step alpha. And the problem we reduce to some first-order nonlinear ODE. So we're trying to find y of z, and f and g are specified by the step angle. And what we want is the full trans series expansion of the free surface y. So you have your waveless waveless resurgence series, and then the trans series bits, which will give us waves and a higher Fourier modes of waves as we sum over chi. Or in the Borel plane, so after doing a Borel transform, we're looking for parametric holomorphic functions of this form that solve the Borel transform of that equation we started with. To solve this PD with the convolution and this initial data. So, yeah, the idea of this holomorphic inner-outer matching that I talked about is that, so these y's here, these are all the higher components. So these are like amplitude corrections to each Fourier mode in your trans series. So going down is exponential order, so higher Fourier modes, and going across are amplitude corrections to the wave. And what happens when you make this kind of singularity ansatz in the Borel plane into that PD is you learn differential equations for all of these components. But you then need to fix initial data for these functions. So you can see they're all missing these. And this is the kind of hard, this is where all the hardness is to determine these constants. That's a hard problem of analytic continuation, which you have to do numerically. So yeah, this is what you learn for the water-wave problem, a bunch of functions in the trans series, and you can try and fix the constants. But I mean, the constants are physically important because they're amplitudes of far-field waves. So what you can do is this, as I said earlier, instead of expanding, as we did just a moment ago about the Borel singularities, we expand about the physical singularities and compare the two. And what you get there is like a sequence of now one variable Borel transforms by 0 of s, by 1 of s, by 2 of s. And these each solve their own Borel PDs. And so what we obtain is like a sequence of problems of the type that I discussed at the beginning of this talk. So a sequence of constant resurgent problems. And as we solve each one, we can learn more initial data of the trans series. So there's a whole kind of nested structure of constant resurgent problems to solve in a singly preserved case. So what you can do then is make, I mean, everything is convergent here. I'm working the Borel plane, so I can look for, I mean, this is a kind of integral differential PD, sort of convolution term. I've got two convolution terms. Probably should be a derivative somewhere. Maybe that should be a derivative. But you can seek a power series solution and then start to understand I mean, what you need to do is understand analytic continuation of that power series from, say, 100 coefficients. Because that's what you can get in practice. And that's where the numerics come in. So there's some numbers for this particular wave problem. So you can start to, like, as I said, this Darboux theorem I talked about earlier, what you just need to do is get 100 of these and then fit the asymptotics of them. And you can learn about the coefficients in the expansion near the singular point. And these fix for you the undetermined constants in the trans series. So, yeah, there's kind of an optimal way to do this for each inner problem. And you can, yeah, maybe I won't go into the details of this because we're running low on time, but for each phi naught of s, phi 1 of s, these inner Borel PDs, you need to understand the analytic continuation, and there's a way to, in constant resurgence, there's a way to remove each singularity by a conformal map, and then a convolution to delete it, and then iterate, so you can probe the higher components, but yeah, I'll leave that. There's some fun puzzle that happens with the wave problem, for example. So if you study just a linear order exponential correction to the free surface, what you find is that there's some step heights. So think of this as roughly the step height. It's not normalized very well, but this is the step height and this is the step height. And what you find is that there's some step heights where the free surface ripples vanish and turn off. But if you actually study the entire trans series and not just the linear order exponential asymptotics, you find that at those points, the higher Fourier mode is still in them, and these two amplitudes interlace each other. So when this one vanishes, there's a third one that turns on again. So you can never truly get a waveless free surface as you go this step higher. That's one nice result of this machinery. I mean, I talked about a kind of a toy water wave problem, but everything I said applies to any singly perturbed nonlinear OE. This is just an illustrative example. I think, yeah, that's pretty much what I was going to say. So the main point was that you can think of parametric resurgence as a sequence of constant resurgent problems, and you can solve each one numerically to learn about the full trans-series, if you like. And if you want to learn more about the full trans-series, you have to solve more inner problems. And I explained how Van Dijk's rule in inner outer matching could be translated to the parametric Borel plane. Hopefully I gave at least a hint of how to apply this in practice, but if anyone's interested in the details, we can talk more. But yeah, thanks very much for listening. That's the end.
Much for the thought, and left some hands for questions.
Okay, can I ask a question?
They are exactly Stokes multipliers, but they are for the higher trans-series components as well.
Yeah.
So you have a Stokes constant for the linear exponential.
Can you?
Minus 2 chi, minus 4 chi, also have their own Stokes constant.
So this is one of the advantages of this approach as opposed to the WKB.
Exactly. Normal sort of optimal truncation allows you to get the first one. But if you instead Borel transform and expand these physical singularities that I talk about, you can get a sequence of problems which you can study. And by analytically continuing those numerically, you can learn about all the Stokes constants in the entire trans-series.
So is this like higher order Stokes phenomenon?
That's a slightly different thing.
Okay.
This is like just the all orders parametric trans-series. I would say something else, which is what I was talking about earlier at coffee.
Yeah.
That was how I would say phenomena. Yeah.
Can I ask a question about Van Dyke?
Those Stokes constants really. The outer problem, or the outer Borel PD, just gives you a sequence of ODEs. I mean, fine, they might be hard to solve, but you know they're singular points. They're asymptotics. The difficult bit is to kind of fill in that structure with constants, and that's where the hard problem of analytic continuation lies. Because you have, essentially what you have is 100 power series coefficients, and to get the higher trans-series component, you might have like an array of singularities. I need to walk all the way out to the fifth one and see what it looks like locally, and that's the difficult bit.
So this is somehow going beyond that WKB approach of
right.
John Chapman did.
Exactly.
Yeah.
It's going beyond that, but to get the whole entire trans-series.
Yeah.
So it's like beyond all orders.
So for a given problem, should you be worrying about this?
Depends what kind of question you answer.
Okay. Yeah.
Like in this example, you might conclude from that method that there's some step angles where the free surface waves turn off, but they don't. It's just a leading Fourier mode turns off. But when that one turns off, there's a higher Fourier mode that's still on. Yeah. And that's the kind of things that the full trans-series tells you. Yeah. In the Froude number, F. That's a good question. Oh, the amplitude will be determined by these Stokes constants, these C's. This is essentially the amplitude of
So it's
order one. Yeah, exactly, order one. Order one in the Froude number. That depends on. Let's go to the previous slide, I can tell you. Okay, so you have look like this. So this is the one in war, I guess. They're exponentially small in the Froude number. That's the only parameter I have. So they're small, yeah. Yeah, they're small in Froude.
in practice, okay. So
No, no. Yeah, very much. Oh, in practice, no. No. I'm not quite sure what in practice means. For me, that's just a toy nonlinear ODE.
Experiment,
It's an interesting question. I'd like to know. I don't know. That'd be cool. I mean, yeah, the exponentially small one is one thing, but I'm talking about so e to the minus chi over epsilon, but also e to the minus 2 chi over epsilon, 3 chi over epsilon, which exponentially small orders smaller. So I don't think you'd see those. Yeah, I don't know how big they are in real numbers. This would be fun to think about. Yeah.
Those are not decaying.
What's that?
Whatever wave. They're not decaying.
Not decaying. You have a far field. It's just constant profile eventually. Exactly.
Or what if it's simple tension or something like that? Do you change the problem?
Yeah, this is without surface tension. Yeah, I don't know.
There's other complications.
Yeah, another complication. The thing is, then I'm not going to get a nice singly perturbed nonlinear ODE anymore. I'll have a horrible non-local term. It's a bit more difficult to deal with. But surely it'll have some trans-series expansion. I can't answer if in the far field it's still constant or not. Maybe not. It might decay. It would be something you could study in principle. You can still make a trans-series ansatz and start to fit all these things. I haven't done that. It'd be cool. Yeah.
Good line. No question online. So if you don't have any more questions, if you don't want to say any more, I think we can go for coffee again and maybe have a little more a chat if you guys want. Yeah, let's thank again someone for coming here.